So for this problem, let's take A and B, which are distinct points in R3, and let's let R to be any number larger than 0. And I want to show that the set S, which contains all points P in R3, such that the distance between P and A is equal to R times the distance between P and B, is a sphere whenever R is not equal to 1, and is going to be a plane if R is equal to 1. So here I'm just going to use D to represent the distance. So here's a initial observation. So notice that if I have just any 2 points in R3, I can always shift them back onto the x-axis, right? So I'm drawing R2 here, but it's the exact same reasoning in R3. So I have these 2 points, say A and B, in my space. I can always move them around to here, right? I can always move them back to be on my x-axis. And so any conclusion that I make regarding sets of points that only have to do with the distance between A and B, I can prove it for these 2 points on the x-axis, and I can just translate it back to my arbitrary point A and B. So without loss of generality, we can assume that my A is equal to negative A0, 0, and B to be A0, 0. So I can just move my points A and B to be equally spaced on my x-axis. I can just move them back. And if I can show that for these 2 specific points, where A is larger than 0, that the statement holds, then for my arbitrary points A and B, my statement must also hold, because it's just a translation and nothing has changed. Right, and so let's start with the condition that the distance between P and A is equal to R times the distance between P and B. And let's just put P to be equal to X, Y, and Z. And so the distance formula is just going to be square root of x, because A is minus A, so x minus minus A will be x plus A squared, plus y squared plus z squared, all square root, equal to R times square root of x minus A squared plus y squared plus z squared. And we can now square both sides to get x plus A squared plus y squared plus z squared is equal to R squared times x minus A squared plus y squared plus z squared. Great, now we can just open up the parentheses, getting x squared plus 2ax plus a squared plus y squared plus z squared equals R squared all times x squared minus 2ax plus a squared plus y squared plus z squared. So now notice that if my r is equal to 1, then my x squared here, a squared here, y squared here, y squared, z squared, on both sides, they all cancel, right? So then we get 2ax is equal to negative 2ax. And because our a is non-zero, we can divide both sides by 2a. So x is negative x, and so x must be 0. And if x is 0, we have my set S is going to be all points P equals x, y, z, such that x equals 0. But then this is just my yz plane. And so this indeed, when r equals 0, is a plane. So now let's consider the case where r is non-zero, not equal to 1. Then what we get is just calling the equations here. We can just expand out the parentheses here on the right, and we can group terms to get 1 minus r squared, x squared, plus 1 minus r squared, y squared, plus 1 minus r squared, z squared, plus 2a times 1 plus and another x, and plus a squared 1 minus r squared equal to 0. And since r is not equal to 1, 1 minus r squared cannot be 0. So we can divide both sides by 1 minus r squared. So we get x squared plus y squared plus z squared plus 2a times 1 plus r squared over 1 minus r squared x plus a squared equals 0. And so we can use these three terms to complete the square for x. And we eventually will get something of the form x minus h squared plus y squared plus z squared equals some big R squared. What exactly is h and big R doesn't matter here, because if you do the completion of the square, we will just get a equation for the sphere. And so this completes the proof.